in France. He writes messages in French. So check this out. Oh, thank you, Brandon. Oh, you can't see that, can you? So what I've done. This is not the bike data. I didn't unfortunately have enough time to create different distributions of, because I don't even know what our data looks like yet. We may have to look at our data and throw out some outliers, right? We didn't even look at that yet. We'll take a peek momentarily. What I did was I created two uniform distributions in yellow and blue. Now you might remember uniform distributions from back in the day. What does uniform distribution mean? We'll see it again next week in case you've forgotten it completely. The likelihood of any event is? The same, dependent, regardless of the event. So, in other words, getting 0 to 5 is just as likely as getting 5 to 10, is just as likely as getting 10. Think of rolling a single die. Every outcome is exactly the same, okay? Think of an iPod randomizer. This is what we'll test next week. When you shake an iPod, you should get, depending on how many songs you have, each song should show up roughly the same percentage of time. Good, we'll test it next week, I promise, JC. That's on the docket for chi-square. So what I've done here is, I've done a simulation that just keeps simulating. Here are the two uniform distributions, random betweens. But I've made it be so that this guy always picks numbers between 1 and 50, and this guy always picks numbers between 51 and 100. So they're picking from, oops, cancel. They're picking from the same range of values, but they're picking differently. One's low, one's high. Okay? Now the green thing in the back is the distribution of the differences of the two variables, which is essentially what we're looking at right now with my brakes. We're looking at the differences in the two averages, yes? So if we were looking, if this, for example, were the cantilever brakes, actually, I think this would be the cantilever brakes, V-brakes, the distribution I would need to use is the one on the back, which is the difference in the two distributions. Make that connection right now before we go any further. Let's make sure we make that connection. So in other words, we have two populations. We think we have a cantilever population and a V-brake population. We think that. I'm going to put the cantilevers over here in blue. I'm only doing that because that's bigger. And we think the V's are over here in yellow.
Should we change our graphs then?
No, leave. This graph is a generalization. Your graph is specific. No, this is perfect because of how we defined our variable. So the back, and now watch Deanne. This will give me 2 minutes, and I'll put that concern to rest. The graph in the back, the green one in the back represents the difference of the two, which is what we're actually testing. So Stacy, here's our two populations. We've knocked it down to 1. Maintain confidence. Yay us. Yay us. Go ahead, Renee, please.
How do you know which data point to subtract?
It doesn't matter. This is Deanne's question too. Thank you guys. Ladies, this is a great question. Deanne was concerned because I did x1 minus x2 instead of x2 minus x1. Now technically speaking, the way we've labeled it on the board is backwards. Check this out. Here are the averages of those two. One's positive, one's negative, but that makes perfect sense. But look at the variances. There's no difference in variance. If I were to graph the other one, it would be way the hell over there, but would have the exact same shape as that one. Which means there's no difference in spread. That's why it doesn't matter. Leave your graph exactly as it is. Whatever we're discovering right now will hold for ours as well. You don't have to believe me. Believe the mathematics. Believe the fact. Look at these numbers. Difference, even the sum has the same variance. I'm going to hold down F9. Kate, ask me that question. I'm going to get the stapler on F9.
I was going to say, doesn't it not matter which one you decide to be
Nope.
X1 and X2 as long as you continue to keep
Not at all.
X1 and X1?
This is just mathematical. This is just a mathematical assertion of that. Hang on one second. Yeah, you're absolutely correct.
It's kind of like, what was, God, it was in high school. I think it's like the distance formula with X1
Yes,
and X2.
exactly.
It doesn't matter as long as you continue.
Define 1 and define 2, and stay consistent with it.
Yeah.
You've got it. You've hit it right on the head.
It is the distance formula, right?
It is.
Okay.
Many formulas, the slope is like that too, as long as you define it consistently and stuck with it all as well. So I've defined the one I've grabbed, and it's updating every once in a while, and notice it's changing. It's changing, but it's beginning to hone in. They're beginning to hone in on values as it's changing. Now, the average of x1 hopefully makes sense. It's directly in the middle of 1 and 50. Okay, it's flip-flopping back and forth 25 and 26. We're happy with that, yeah, it should be there. And the average of x2, 76, that's right where it should be. The averages should be here and here, shouldn't they? So if the average of this one is here, and the average of this one is here, and I subtract this one minus this one, doesn't it make perfect sense? It should be negative 50. Which tells us that the top part of our test statistic is freaking perfect. Because we're testing exactly where it should be. But we knew that before we even started. We knew that by the central limit theorem. We are guaranteed accuracy. We knew that. We guaranteed accuracy. The bell curve is always going to sit right on top of where the average should be, which happens to be right there. That's where the green curve is sitting. Everybody cool with that?
So it should be n1 minus n.
Now the question is, what's down the bottom? Now, you might be a little concerned with the word I used right here, variance.
Well, that makes sense.
I didn't call it standard deviation though.
Different.
I called it variance. Remember what variance is versus standard deviation? I bring it up once every 4 weeks in here.
Difference between the amount.
It's related to the standard deviation, and you've probably forgotten how, and that's okay. It's the blank of the standard deviation. Stacy, you actually said it earlier. It's the square of the standard deviation. Now, I didn't look at the standard deviation. I'm going to come back to why I didn't do that. What do you notice about the variance of the distribution we need and the other two variances?
Half.
What do you notice about it? And it's going to have to be an ish. It won't be perfect because the thing go off to infinity. What do you notice about that number versus the... It's them added together.
Yeah.
That is the key we need to figure out what the standard error is. We need to know that when you start adding and subtracting random variables like we just did, you add their variances. You don't subtract them. It seems to make sense. You'd think you would subtract them. If you subtract the random value, you subtract the variances. Well, that means that whatever error you have is getting less. Wouldn't the error have to go up? You'd have to increase the error, wouldn't you? Because you're taking two measurements versus one measurement. So clearly, every measurement has error. So the error has to go up. The key is, how much does it go up? That tells us the answer. It adds them together. I'm going to mute this and swing back over to this board. We now have our answer, friends. We now have our answer. You might not realize we have our answer. But this gives us the answer. The fact that that beautiful green curve, you see how it stretches twice the size of the yellow and blue? There's your standard deviation if you think about it that way. That green curve stretches from all the way left to all the way right. That's twice each of those, isn't it? So it's actually both of them added together. It's whatever the variance is in this one, added to whatever the variance is in that one, makes up the variance in the green one.
So we're kind of like two curves added together.
It's exactly what it is.
So would it be the square root of the n plus the n1
Oh. Okay, say it again.
So
Brandon, if you don't mind.
it would be the overall square root
Oh, yes.
of 1 minus, or plus n2.
Oh. But we don't forget the standard deviations too.
Yeah.
So, yeah, yes, Kate, you've got it. Now, realize, let's write it first. This is what is going to be happening. That. And then the variances have to be added together. This technically is a standard deviation, but I can write it a different way. That's the same thing mathematically. That's the square root of the variance becomes the standard deviation. All I gotta do is make one of these for each of the two samples and I'm done. It's S1 squared over N1, that's the variance of the first one, plus S2 squared over N2. That's the variance for the second one. There's your standard error. Freaking rad.
Oh, that is awesome.
I think so.
I can't, I want to be able to sleep today.
Well, I can't. Actually, I will be exhausted by then. You got it! That's it, you're done now. Now, I will never ever ask you to compute one of these manually. Why? Why would I? That's just torture.
You should
Why?
So we'll remember.
No, why do you need to remember? You never need to remember this. You need to know what the black box is vomiting out to you. And you need to know what is coming out of the test. No, you're practicing the wrong thing if you're practicing what numbers are there. You guys graduated Math 20. This is Math 20. Knowing that it has to be there is the Math 244 part.
Right, but it'll help concrete it all.
It won't. I've got 20 years of practice watching students not learn it that way.
Well, if you're
Trust
doing
me.
it by hand, there's a lot of you accidentally put in the wrong thing, you put in the parentheses in the wrong place, you.
Because Deanne, now you're right, but here's the other problem, Deanne. If you want to do it by hand, okay, totally fine. You want to do it by hand, you have to do this by hand too. You gotta fire up the internet
You
here.
will always have a calculator.
Yes, you will.
Dude, I always
You
think
will.
about it.
You will. I mean, that's the thing. If you're doing real statistics, you will have a calculator.
Right?
If you're doing statistics without a calculator, you're not going to get hired.
Well, I don't want to do that.
Well, then you won't be doing statistics. Satterweight. Brandon, if you don't mind killing that again, thank you. Satterweights. Where is it? Satterweights formula for. Oh no. Oh yeah, there it is. Okay. So if well, that's not right. Satterweights degrees of freedom. There we go. And let's get images. There he is. Okay. So by all means, if you want to do stuff by hand,
Which means,
you can, but that means you also have to calculate that by hand.
Yes.
Because that is how you get the t-score that you need on the curve. Okay? Deanne, the way it used to be isn't always the way it should be. That is a pain in the ass. And students mess it up. I made students 1 year calculate Satterweights. This is how you do degree. There's a very simple definition of degrees of freedom. It's usually one less than the sample size. One less than the sample size. The problem is you have two sample sizes. You no longer have one. This is the way of figuring out what the degrees of freedom are now. Look at that freaking thing!
I think you should be done by candlelight too.
That's totally fine. By all means, make sure you got a nice sized candle and a lot of chalk. And maybe a bearskin rug to lay on while you're doing it. The idea is you do not do this stuff by hand because you would spend half an hour doing it and you probably do it wrong. We let technology get the results and we interpret what they are. That's the point. That's the point. Okay, let's pause, grab your TIs, because now we're ready. Now we know what's coming out to us. We know what's coming out to us. It's a forest trees argument, Dan. Your point is well taken. When I got out of college 20 years ago, I vowed that my students would not use technology. They would do everything manually. And I realized 5 years in, I'm like, that's dumb. The world doesn't work that way. My belief was you should be able to do everything by hand. Yes, if I'm training math majors. But I'm not training math majors. How many math majors? We got one.
You have to do it
We'll
all
talk
by
afterwards.
hand.
Yeah, Lars do it all by hand. But the idea is, once you get done calculating Satterweights and that manually, you then have to know what the result means. That's the only important thing for statistics. So, grab your TI. Grab your TI. Let's make sure we're zoomed in where we need to be zoomed in on, which we're not right now. Have shoes. Okay.
Speaking of technology, when are they going to update that thing?
Well, my goal is to get you all guys all into a computer lab. We shouldn't be using these things at all. I mean, they're great for what they do. They are great for what they do. In other words, they do the t-tests wonderfully. Excel actually does a worse t-test than your TI. But until we can get into a computer lab, we're
I
screwed.
meant the lovely plug-in.
Oh, this whole thing? Well, it's all part and parcel, unfortunately. I do want to do one thing quickly. Can I make 2 quick box plots on our data to see if we have any goofy data? I want to make sure we don't have any outliers that are going to pull our averages anyway. Because this is something Michael's got me thinking about now after you said it about 2 or 3 days ago. I mean, outliers are a reality with average data. They're not a reality with proportion data at all, but they are a reality with average data.
What if
So,
we have like instinctually thrown out the outlier with the 14.4 on the skin? We all kind of felt upset about it.
Yeah.
that's fine, but realize why I threw that one out. It's technically a different data point than the rest of them. I'm talking about ones now that are too big, even though they're part of the same data set. But they're unusually large or small. Yeah, I instinctually bad about that. So I'm just going to make some quick box plots, if that's okay with you guys. Somebody asked me an awesome question about frequency of the data. These are all raw data points. So your frequencies are all going to be 1 on them. Raw data points, yeah. Frequencies are all 1, for sure. For sure. So there's L1, that's my cantilevers. Here's plot 2, I'm going to go with L2. That's my V's, better turn it on too. Alright, and let's just make sure nothing's on. Yep, we're good there. Okay! So here are my V brakes.
I don't see any,
I don't either. There are my cantilevers. What's awesome about looking at them this way is, I don't see any outliers. That rests my rest of my concern about the 14.4, which are taking the 14.4 out. What else do you notice? And this very rarely happens in real data sets. There's absolutely no overlap of the data at all. None. Even the tails, the high tail of the one doesn't overlap the low tail. These aren't confidence intervals, in other words. These aren't confidence. This is the actual data itself. Many times, you can have non-overlapping confidence intervals, but the data itself overlaps. This one doesn't have data overlapping, which reinforces the belief that we've got a big old difference between the V-brakes and the cantilevers. Yeah, this is cool. This doesn't happen very often. Yeah, good stuff. Good so far? All right, beautiful. I think we're ready to test the damn stuff now. I would test it for bell-shapedness, but I'm worried more about outliers than bell-shaped. I don't care about bell-shaped. It's pretty resistant to that anyway. So over to tests. Lauren, here's your 2 sample t-tests for sure. And it's going to be crunching out. It's going to be crunching out exactly that test statistic for us. And we're going to be expecting a positive one now, based on what we just saw on that graph. We're going to want a t-score that's positive. 2 sample t, we have data. Oh look, everything's pretty much right. List 1, list 2, L1, L2, yes. Frequency 1, frequency 2, 1 and 1. Good so far. Pick your sign correctly. Pick your sign. That's why we have you write HA out, so we're going to greater than. Pick it, go ahead, pick less than. There's greater than.
Okay.
Yeah, there's greater than. Fair? This right here, Lauren, you asked me this last time. Leave this on no. Here's why. But this goes back to what Deanne actually was talking about. Back in the day, when these calculations were done more by hand than by technology, very often statisticians would what's called pool the standard deviations, or the variances actually, of the distributions. They would say, you know what, let's assume the variances are the same, because it makes the math easier. And you can see why that would make the math easier. It makes the S1 and S2 equal, which makes the mathematics a little bit easier to deal with. Now, with technology, there's no reason to do that. It's doing the math for you. And not only that, are those variances the same? Assuming my data is representative of what's actually going on with these brakes, those aren't the same. There's a tighter cluster around the V-brakes than the cantilevers. So if I assume they're the same, I'm actually behind the 8 ball right off the bat. So pulling is an antiquated practice. For some reason, well, it doesn't surprise me, it's stuck in the TI. Many things are antiquated, stuck in the TI. So just leave it on no, every step of the way. Cool? Fair enough? At best, you get the same answer you would otherwise. At worst, you get a vastly different answer. So there's the answer you need right there. Okay? So let's go back to test 2 samp t, and then go down to the bottom, calculator draw. Let's draw it. Okay, if there's a difference, we're looking for it up here. We're trying to get past that line in the sand. I don't see it yet. Are the cantilevers better? It's very interesting. 12.5 standard deviations better.
They're not even, their curves aren't even.
They're not even, they're completely different curves. You guys okay with this? Yeah? Look, here's the cantilever curve, right here. Here's the cantilever curve.
It's like they're not even the same brake or something.
Well, they're not. That's the point. Now, where is the V-brake curve? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's alcohol. It's alcohol. There's your V-brakes. Or actually, there's your cantilevers, I guess. That's the V-brakes. Here's the cantilever. It depends on what you put where. They're that far apart from each other. Now, how can they be 12 standard deviations when it's only 8 feet? Because the standard error is so tiny. That's the point. The standard errors are so tiny. That's the advantage of large sample sizes. Even if the sample size is only 20, you're dividing by the square root of 20, which is like 4.5. So whatever the standard deviations are, which as you noticed were already pretty tight, are going to go down by a factor of 4. That's pretty awesome. That's pretty awesome. So, what do we conclude? You've got steps, whatever they are now. I forget the numbering now.
7, 8.
Yep, you've got 6, 7, and 8. Yep, you're testing t. T is, it's telling you the p. Is the p-value really 0? No, it's not really 0. It rounds to 0. Actually, we could probably get the p-value if you're interested. We can run the 2 sample t, but calculate instead of draw. There it is. Yep, your p-value is 0.00000000001. Oh, there's your Satterwave. There's your shadow wave calculation, that ugly ass thing I had on the board about 10 minutes ago, if you want it.
I'm fine just leaving it.
Well, you should. You should. Notice how 29 is somewhere around both of our sample sizes. Our sample sizes were what, 20, well, 20, 21, 19, those were our two sample sizes. So 29 is close to that, but shadow wave gives us that result. Here are your two sample averages. Katie, I got a different answer than you, I apologize. But it's close. I mean, it's basically a difference of 8 or 7, whatever you told me it was. And the point is, it's not that much of a difference. But when you weight it with a standard error, it's all the difference in the world. The standard deviations in the sample are somewhere in here. Here they are, 2 feet and 1 foot. But the standard error in the sample is a half a foot and a quarter of a foot. Start thinking about that. If the standard error is a quarter of a foot and you're going 8 feet, that's 32 standard errors. Does that make sense? Your measuring stick shrinks as your sample sizes go up. That's the whole point of central limit theorem. That's the point of sampling. The higher your sample size, the shorter that standard error stick goes. So you're not using directly these numbers anymore. You're weighting them in that test statistic with the sample sizes. If I replicated all these numbers again and got the exact same data but twice as many of them, that test statistic would get even more extreme because the standard error would then shrink down once again by another factor. And it would get even more different. You've been hearing that since the end of 243. Kate, you said something very, very interesting on the first week of class. No, you said there was a central limit theorem quiz, optional. And you said, we did this for like 2 days in 243. And I said, yes, and you're going to use it every day here in 244. It's probably, between that and distributions, it's the 2 topics we keep referring back to.
And it wasn't 2 days, you threw all that out as the last day of class and said, don't worry about it, we'll cover it in
2 days of class, last week of class. You rolled the dice on the second to last day and we analyzed it on the last day. Because you guys were important to me and I can't tell you how you learn. And I didn't put it on the in-class exam, if you remember, you're welcome. I pay attention to when you guys learn and what you guys are learning. I do pay attention to that. So, but this is the reason. I know that's the bridge over to Math 244. And there we are again, using it again. So, conclusion, it appears that good! V brakes, you're all going to say it differently, it's totally fine. It appears V brakes take significantly less stopping distance, or if you want to say cantilevers take significantly more, totally fine, totally fine. Worse or worse, you can also go with worse, I'm totally fine with that. You might want to practice saying it both ways only because you have to explain it to your neighbor who's a biker who wants to change his brakes out, and then that's not that hard to believe, honestly. You know, dude, V brakes are worse, or V brakes are better. Huh? There's a study. Rule did. Crazy hippie. So, I'm going to have you guys retest it again on your last exam. Because, remember what I told you earlier? No, first of all, what kind of error do we make? We're in that type 1 category, aren't we? We're in that type 1 category, yes? We're in that type 1 category because we have a positive test result. We said there's a difference. Suppose some of you couldn't live with a type 1 error, could you? A few of you said, wait, I don't like, a couple of you said type 1 was worse, a couple of you said type 2 was worse. Who said type 1 was worse? Good. Now, if at the outset of the study, you really, really, really want to avoid a type 1 error, we can't do it now because the study's over. But in the beginning, what could you have done to avoid a type 1 error? If you don't care about a type 2. Did you hear that? Raise the confidence. What would that do? What effect would that have?
Type 1 error further.
It would take, you can't see this. Yes, essentially what that would do is it changes this line in the sand. This line in the sand would no longer be trapping 5% at 95%. You'd have to move it over to say 99% and 1. Higher burden of proof for change. In other words, the brakes would have to show more of a difference in order to trigger a significant change.
Is there a way to do a two-tailed test at higher confidence where you get one on each side?
Absolutely. We could have done this one two-tailed. Just look for a difference. And all that will do is it pushes them both out like this, Lauren. So, and the different... But
Have a lower, like it would only be 98% confident as opposed to 99% confident with the one-tailed test.
if you go 99% confident with a two-tailed,
Yeah.
then you'll have a half and half.
Oh, okay.
Just split the difference evenly across. Is that fair? And I remember a prof I had in undergrad. I was this alpha over 2 guy. Remember how type 1 error is called alpha? It's one of those statistical symbols. I would always be like, I asked the same question you did, and he started calling me alpha over 2 guy. Because you take the alpha, divide it by 2, and put it at the tail. So he would always point to me. Vince Larisha. Love you, Vince. He's the one that told me, though, if you remember, his favorite football team flipped heads 13 times in a row on the coin toss, beginning of the game. His favorite football team flipped heads 13 times, and then he asked us, what would you bet on next? Trying to trick us into saying, we feel good about tails. And we all said, dude, it's 50-50. And he's like, yep, but I'd bet on tails. And I'm like, dude, you have a doctorate in statistics. How can you say that? And then I realized, because he's being Vince. I'm an over 2 guy. So, yes, that's all you'd have to do. But the beauty of it, again, Lauren, the beauty of all of that, and this ties back to Deanna's question too. Well, it's when it's on. This tells you, thank you. This tells you everything you need to know. Right now my battery's real low. This gives you the results of what you need. The important part of what you're doing is not crunching that, or God forbid that saddle race thing. The important thing is knowing what the results coming back mean. That's always the most important thing. I'm going to have you guys I know I gotta change your batteries. I'm going to have you guys revisit this on your last exam because I have to collect the data. I'm waiting for a day when it's similar conditions to when I tested with Max my brakes. And here's why. Remember how I told you when I went on the online forums, they said you can't run full-size V-brakes, only mini Vs. Well, so it started raining a couple weeks ago. I wanted to put fenders on my bike because I'm tired of my butt getting wet every time I ride in the rain. Get the fenders from Repeat Performance, and the guy looks at my bike. I'm like, I bought this bike from you guys, but I put different brakes on it. I'm like, yes. And he said, these fenders will fit. I'm like, but I got mini Vs. Are they going to fit under? No problem, they're going to fit under. Guess what? It didn't fit under. I got them home. I'm like, son of a bitch. So then I start modding them out. I'm like, time out. Let's not mod something so I can't return it for something that'll work. And then I started thinking, I'm like, you know what? I wonder if full-size V-brakes will work instead of short ones. Because all the arguments were the extra 3/4 of an inch creates a physical advantage. I'm thinking, it's not that much, especially when spread over an entire brake cable. So, a couple weekends ago, got up at 4 a.m. instead of 5 like I usually do on Saturday, went down to the garage, did an experiment. Threw my full-size V-brakes on the front of my bike, left the short ones on the back, went for a ride around the neighborhood. Guess what? They work better, I think, than the mini Vs because they have more stopping power, not a whole lot more, but they work a little better, at least as far as I can tell. But that was extraordinarily anecdotal, so what I'm going to do, assuming the friggin' weather ever dries out again, I'm going to rerun the test, collect another 20 or 25 data points with Max, and have you guys compare all 3 data sets. Now, you cannot do that with a t-test. As soon as you go above 2, you can't do a t-test anymore. You need something called an ANOVA. That's the F distribution. That's one of the last things we'll do in here together, is that particular test. It's called an ANOVA. Testing all 3 to maintain Stacy's confidence. Jack, you're going to say something. Go ahead.
After class.
Okay, excellent. So, look forward to that. And when I said look forward to that, you might not look forward to that. But that's one of the things you'll be doing on your last exam is analyzing both these data sets, plus the third, which I haven't collected yet. And we're going to see if that set of V-brakes rises above the other 2. Or if arguably my gut was wrong, false positive as it sometimes can be when I get excited about something. And it's no better than the mini Vs. Maybe it's no better. But I gotta wait for the right conditions. I can't do it right now because clearly I'm gonna have 35-foot stopping distances. Only because my neighbor's garage is 35 feet from that driveway and I'll crash into it every time because the ground is icy. So, okie doke? That's it for today. Don't turn that one in. Hold on to that one. We'll do a few more on Monday. We'll turn those in. Only because I want you to have this one in front of you. It's the first one. Say that again. Dude, you're gonna have at least 6 more possibly between now and the end of the term.
Good, okay.
I've got 3 planned for next week on the web, plus whatever we turn in class. And I've got at least 2 planned for the final week. I'm watching your guys' numbers. I'm watching. Tim, did you get my email?
Yeah.
Just fire me all those grades.
I wrote it down on here.
Even better. Put them right here. Even better. I don't know what the hell happened there. There was a network outage while I was doing it. I started sports. I'm guessing maybe something got broke in your line. What's that?
The discs fail at once?
No, because everybody's data was fine except for Tim's. All of Tim's
I mean with the network.
I know, but no, because everyone else made it was fine except for Tim's. So Tim's discs failed.